Hello, everyone. Welcome to another BAF event. Today, I'm very happy to have with me a good friend of mine. We've been working together for the past 6 months, Shamir. He's the president of the Student Project Initiative at University of Adelaide. It's a great group of student developers that are working on some very cool stuff. And today, we're actually talking a lot about blockchain development, different programming languages. We have a great, oh, there he is. Hey, Jay, how's it going? Jay is one of the co-founders of Reach and CTO. I let Shamir introduce Jay more properly. And yeah, enjoy the chat and I'll see you in networking.
Cool. Hi, everyone. I'm Shamir, as PG introduced me. I'm one of the co-founders of SPI. We've been building some pretty cool use cases on blockchain. So we're going to be talking about Reach. It's a programming language that's been created for, make Dapp development much easier and much more fun. And let's just get started. So Jay, I have a few questions actually. So firstly, can you tell all of us about your academic background and how you got into blockchain and what made you decide to fund a company?
Sure, yeah. So my academic background. So I did my undergrad at the University of Massachusetts Lowell, and then I did my PhD. This is in computer science under Sriram Krishnamurthy at Brown University. And when I was at Brown, my main research was on basically what I did is I made a programming language for cryptographic protocols, specializing in ones that are like authentication protocols. And with this programming language, I built a verified compiler that compiled the programming language to OCaml, and it used Coq and a traditional verified compilation model. And I did a bunch of analyses on that. And then after I finished that, my dissertation, then I became a professor of computer science in Utah at Brigham Young University. And I stayed there for about 6 years. And then I moved actually to, well, first to Vassar temporarily, and then to UMass Lowell as an associate professor, which is where I got tenure and which is where I am now. So it's kind of fun being back at my, alma mater. And so that basically is like, 15 years. So, I started as a professor back in, I guess, 2006 or 7 or 8, somewhere back there. And this whole time, I've basically been working kind of 2 kinds of research. One on programming language design. In particular, I've been really interested in systems and web-oriented distributed systems. So some people may have heard of the programming language Racket, which is, I'm one of the developers of that. I'm not one of the creators. Basically, I'm sort of like the 2nd generation of academics making the Racket programming language. And I'm one of the managers of that. And then kind of the other strand of research was on verification in general. And so I've done work on doing what I call performance verification. So being able to like look at a program and being able to prove mechanically that it has like an expected runtime. I worked on this system that's called temporal contracts, which is a way of doing runtime monitoring to verify any property of a program. So anyway, so I've sort of done a large variety of research. And how did I get interested in blockchain? I don't know, maybe back in like 2010-ish, I first heard about Bitcoin. And I heard about it in the context of basically like, I'm very interested in technology that empowers individuals to get out from underneath sort of like the influence of the powerful. I'm trying to be like politic in saying this, but that's something that's always been a passion of mine. Yeah. And that's the context that I originally heard about Bitcoin. And then I didn't really learn very much about blockchain in general for quite a long time. But then eventually a good friend of mine So basically, maybe one of my oldest friends, maybe like 20 years now, we've known each other. He was working on a company that was doing blockchain stuff. Well, actually, I had previously met with some people that were starting their own consensus network, and they asked me for some advice from like a verification angle, and that's when I first like really learned about smart contracts. But then this friend that kind of pulled me into it more, and I don't know, we just had lots of conversations, and they were building a program. They were building like a scaling solution. So rather than trying to build like their own network, they wanted to build like a layer 2 that had interesting properties. And we had a lot of conversations about like, how would you know if that program was right? And that really got me interested more. And I realized that a lot of my previous like academic and research preparation really prepared me for being able to combine all sorts of different aspects of my research into one thing, and that thing basically is Reach. This friend in this company, I did a little bit of consulting for them, and then that company split up because basically people in it, some of them wanted to work on the scaling solution, some of them wanted to work on like a development platform, and so they all kind of, you know, went their different ways. And then with Chris Swinner, who was one of the people in that previous company, him and I started Reach to build the development platform that we believe is the one that will be the future of blockchain development. And from kind of like a research perspective, essentially what Reach is the grown-up version of my PhD dissertation back, from 16 years ago or whatever, where that had a very simple model of what an authentication protocol was for, and it compiled to OCaml. And I've basically taken that and made it so that rather than compiling to OCaml and being verified with strand spaces and implemented in Coq, now what it does is it compiles to JavaScript, Ethereum, Algorand, and targets the blockchain space and has basically more computational complexity than just an authentication protocol. And that was back in September 2019. And we basically, spent maybe like 6 months or so building like the core prototype of the language, maybe a little bit earlier than that. And then we spent kind of a long time sort of like filling out some of the features, working on the documentation, and we kind of did like our launch back in September 2020. And that's when we really tried to push hard, having people learn more about the language. I built, the document, I wrote the documentation, everything like that. And ever since then, since September 2020, we've been growing about maybe like 10% every week or so. So we've got maybe like 500 or 600 or something, I forget exactly, developers who have tried it out. So anyways, that's kind of a long answer to your short question, Shamir. Hopefully you have more questions.
Yeah, no, definitely. That was a great question, answer. And also, I think you have like amazing qualifications for just, building something like this. So just for the audience, can you give them just examples of what the current state of blockchain programming is like, and why are there so many languages? And why would you even need a blockchain specific programming language?
Yeah. Okay. So ignore what's on my screen. I'm just going to be talking. So let's just imagine that you're just going to write like a totally vanilla like terminal program where we're just talking like normal program development, the way that you would do it, and when you're making, I don't know, like a simple like chess program or something like that for your undergraduate course. In this, even the most basic programs tend to be interactive systems where you interact with files, you interact with users, you interact with other network services, and so on. And from that perspective, you could just imagine that like, oh, well, blockchain programs are just exactly the same as normal programs. It's just that they run on a special computer, where that special computer is, the world computer of the Ethereum computer. And I'm going to describe things, when we say like existing development, I'm going to talk really focusing on Ethereum, because although there are other platforms that have smart contracts, Ethereum is really the platform that has the most advanced development. So I think that it's the most representative. Okay, so one way you could just think about it is that, well, we have the universal, world computer of Ethereum, and then we just run normal programs on it. So that is the world that could plausibly exist, but there's all sorts of little details about that don't really work out. And one of the core ones is that if you have this world computer, then everyone needs to be part of running it. And since them being part of running it means that they need to, like, when you run your program on the world computer, you're like burning the cycles of someone in China, you know what I mean? Or someone in Iceland. And so you gotta pay for the privilege of having them run your program. Now, we could just imagine that we could take a totally normal programming language and then just basically add like a little tick counter that says, as time goes on, you have to pay more. And so this is the concept of gas. And we could have designed the like Ethereum virtual machine or something like that in a similar way. But some operations, they may be more expensive than others. There's also this whole issue of when you're running a program on your computer, you've got your disk and you have memory and you have like ephemeral registers and things like that. And so the current blockchain programming model is that all of those different things are going to take different amounts of time to and different costs to do. And that's going to impose restrictions on what kind of programs are reasonable to run. And in particular, it's going to impose this constraint that we're going to want to be able to predict how long the program will take to run. We have a much constrained effect model. So like rather than being able to like just arbitrarily open network ports and modify files and stuff like that, all of those things are going to have to be greatly constricted. And all of these things basically force the blockchain programs to feel very different than normal programs. Now, if blockchain programs had been made first by programming language theorists, we would have a network that's very similar to Cardano probably, because we would have the blockchain monad where we would enumerate all of the effects that a blockchain program can take, and then those would be carefully described that way. Instead, what's most predominant is like a virtual machine model where you program to this virtual machine, and the virtual machine has all sorts of like bespoke restrictions that make it not a compelling target for existing languages. Now, once we know that we're going to have to build something to target this special machine, at that point, we're building a language, so we might as well build a language that has concepts inside of it that are unique to the blockchain domain. And really, I think the core one of those is just the concept that all interactions carry with them value. And when we say value, we mean like the funds of whatever the token is, of whatever the network is. And that's kind of like the big idea. Like if you think about Solidity, the main thing that's going on in Solidity that makes it different from any other programming language is it has this non-uniform memory hierarchy where you have like local variables, memory, and then storage. And that non-uniform memory hierarchy really comes from the fact that there's different gas prices for those. So that's where we see the computation costs influence the language. Then the other thing that happens is we have this assumption in the background that every time you call a function, you're going to send not only values and receive values, but you're going to send funds and receive funds, potentially. Now those two things are like, that's the new idea in the programming language world of blockchain. But there's kind of another angle of it too, which is that like blockchain programs are like REST programs on steroids. And what do I mean by that? So REST, we're talking about when we talk about REST in the web, there's this idea that you can write a microservice that is that you can basically make like a stateless computation where you're like observing little pieces of the network where there's no long-running persistent session. So what do I mean by that? Like if you were to when you use the SSH, the shush protocol, you like send a message and then a message comes back, and you're using this same protocol session over and over and over again so that the connection is stateful. All blockchain programs have to be written in this stateless protocol style, because you're going to, when you send a message to a blockchain program, you're not really starting a long-running computation. You're basically bidding on a spot in the very next time to run a program. And so you're only getting access to that one next slot. And because you're only getting access to that one next slot, you're going to be doing a small amount of work that is going to be saved persistently in the world computer. And then you're going to have to come back later and restore all of the state. So because of that, programming the blockchain program itself, not only do you have to use this new programming language with this non-uniform memory hierarchy, and you have to think about, values, but there's this other side, which is essentially that you have to write REST servers where you don't have any of the conveniences of a platform like Node.js or Flask or anything like that, where you actually have patterns like the async await pattern. Like, what is the async await pattern? It says that I want to do this and then wait for the user to do something and then do this other thing. And what that really does is it means that there's an implicit state variable that says, am I in the first half of the program or the second half of the program? And because the traditional blockchain programming languages don't support something like that, you have to say, aha, my program has 2 steps. So I'm going to pull this part out into function 1, this part out into function 2, introduce a new variable that says, am I past step 1? And have this part say, I got to check to make sure that variable says I'm in part 1. And then when I'm done, I got to set it to be part 2. And then this function says, I got to check to make sure that variable's in part 2, and then change it to the next part. So you basically have to think about your program as being a state machine. And then this is a design that you hold in your brain. So I see, there's a state machine. And then every arrow in that state machine becomes a function in the blockchain program. And then the job of those functions is to validate that they are really, in fact, in that outgoing state, and then make all the effects that bring us to the outgoing state. And then that's what blockchain programming is like. Now, I definitely have just described it from a sort of like programming language theory centric point of view, but all of these issues are the things that actually affect day-to-day blockchain programmers. They have to think about that non-uniform memory hierarchy. They have to reason about not only values, but funds, and they have to reason about this state machine that is implicitly in the background of their program. Now, some traditional programmers, traditional in the sense of like desktop applications, they would look at me and they would say, well, all programs are like that because all programs are state machines, and that's why we use UML diagrams when I'm designing my C++ classes. Like you're just saying that it's just normal programming, and that's true. The only difference, though, is that normal programs can be written synchronously, and they can be written with control flow information latent as part of the state. And that's actually one of the things that makes programming in high-level programming languages like C++ or Python or JavaScript so different from programming in a language like assembly, that you have this control flow information that's implicit in the state of your program that you don't need to reason about. And the big thing that makes blockchain programming with languages like Solidity special is that it is programming without control flow. Now, of course, you have control flow inside of one step, but you don't have control flow across the entire application because that is lost behind the veil of the stateless interaction protocol.
Wow, yeah, that's a great analogy that you've given us. And I think there's a lot of like these operating constraints that a blockchain has that developers don't have to think about, maybe if you're on a desktop, because you don't usually have to worry about memory that much anymore if you're programming in higher level languages. Also the state machine issue as well. So yeah. Let's talk a bit more about Reach.
Let me just pop for just 1 second. The thing that is most similar today are people who are building embedded systems and people who are doing GPU programming. And actually those 2 areas are extremely in vogue right now. because people are very interested in making like small embedded devices that are bespoke for their own purposes. Because we have boards like Arduino, we have like 3D printing to build small things, and then GPU programming also has the same problem of there's this non-uniform memory hierarchy. We have to be extremely explicit, and control flow is possible on GPU kernels, but it's essentially not reasonable. Because it's too expensive and we have to deal with the memory so much more meticulously. So, if you are like in university and you're like, there's no class that's like hardcore blockchain programming yet, take the class that's on hardcore embedded systems or hardcore GPU programming, and that will teach you a lot of the fundamental tools. The professors won't know that they're teaching you blockchain programming, but they are.
That's fascinating that you mention it. I didn't think of it that way.
Yeah, so you were gonna ask another question, Shamir.
Yeah, sure. So I wanted to like focus now a bit more on Reach, and
Sure.
and just let's talk about how it's different from Ethereum, and how you can compile down to different blockchains, if that's the case, and how do you see the future of Reach being developed, and maybe even give us a quick tutorial about how to go about developing on Reach.
Yeah, so I'll give you a little quick example after talking kind of high level. So that whole issue that I said before about, there's this non-uniform memory hierarchy, you have to reason about funds, and you have to program in the state machine. The goal of Reach is to provide the high-level programming language for blockchain. Now, other people would say that they're doing the same thing because they would do something like, oh, I'm going to make it so you can write your blockchain programming, but it's in Python. Or I'm going to make it so you can write your blockchain programming, but it's in OCaml. Now, Python and OCaml are cool programming languages, not as cool as Haskell or Racket, but they're cool. And those high-level programming languages, when you like compile Python to it, what you're still doing is you are still programming with a non-uniform memory hierarchy. You're still programming with a state machine. You just have a more pleasant way of doing that. You're not actually programming with a fundamentally different abstraction. And this is the thing that makes Reach the most different. The thing that is most different about it is it has a totally different abstraction than the one that I just described. Its abstraction is most similar to the UML diagram that you would give for a protocol. So let's just think of a really, really simple example. Now, when most people say, let's think of a simple example for a blockchain program, they're going to be like, let's do a Kickstarter fundraising campaign. That's really simple. Or they'll say something like, let's do an automatic market maker. That's simple. Now, those are simple blockchain programs. But if I go downstairs and I talk to my son, who is learning programming for the first time, he doesn't know what those things are. And my guess is that, if you're in university, your friends who have spent their whole lives basically being like, I'm going to go, do machine learning to analyze, to build the dream of self-driving cars, or I'm going to go build video games. Those are like the two things that my students are the most interested in doing. They have no idea what automatic market makers are. They've probably heard of Kickstarter, but they don't really think about like, what is a crowdfunding campaign? How do I program that? Because these are very intricate domain problems that are of interest today for the blockchain world. So I'm going to give you an example that is a totally stupid domain problem, but it's a domain that you already know. Everybody has already heard of rock, paper, scissors, or Rochambeau, or Mora, these games that are played, with our hands when we're, in grade school. So people know the rules of rock, paper, scissors. How do we play rock, paper, scissors? Well, how it works is I go up to you, Shamir, and I say, I'm going to bet you your lunch that I'm going to win you at rock, paper, scissors. And you're like, I'll take you on for that. So step one, I offer you a challenge. You accept the challenge. And then we simultaneously show our hands. And then we look at our hands and we see, aha, it was a draw. So we go again. And then, the right hand won. And then now the winner's over. So that way of describing the interaction, the way that I just talked about it, that is a UML diagram for a protocol. So when you write that in Reach, it's going to look something like this. So you start off your Reach program by, indicating that it's Reach. You're writing a Reach application. You're going to say who it involves. So When you write authentication protocols, traditionally you use Alice and Bob. There's these cute names. So Alice is going to be one player, Bob will be another. And then inside of these braces right here, we're going to write the program. Let's just jump ahead real fast. And look at the program. Okay, so this program right here is a version of this rock, paper, scissors thing. So the way that it works is we start off by Alice offering up the terms of the game. So she's going to say, here's my wager, and here's what hand I'm going to play, and then she pays on the wager. And then Bob says, aha, here's what I'm going to play, and here's my wager. And then we compute the outcome of the game, and we're going to send off the winnings. Now this program right here is not perfectly the thing that I just described, because it doesn't deal with the fact that we play the hand simultaneously. It doesn't deal with the fact that we want to keep playing until there's not a draw, but it does deal with the fundamental components of the game. And this right here is really actually the entire Reach program. And notice that it has the style of saying, in this interaction, this person does something, and then this person does something, and then we do some reasoning about what happens, and then we're all done. Now, inside of this, we don't say anything about, are we using memory? Are we using persistent state? What are the states of this? How do we derive the state machine? We don't talk about any of those things. Just like when you write a program in C++, you don't talk about register allocation, and you don't talk about exactly modifying stack frames. Those are things that are below your consideration because you want to program at the business logic of whatever your application is. Now, where do the actual values come from? Now, one thing that we could have done with Reach is we could have made it so that when you write a Reach program, you're simultaneously making the user interface. So it could be like a programming language where you're describing what happens on the blockchain and you're describing what happens in your web browser. And so one of the things that I did is I made the decision that we want to make a clear division between the part of the program that is blockchain centric and the part of the program that is just a front end. Let's sort of step back from this for just a moment. In the traditional world, in the, let's call it the classic world of blockchain programming, like with Solidity, every DApp tends to be really three different programs. Step number one is you'll write the smart contract. Program number two is you'll write a middleware layer that'll interact with Web3, and this thing will know exactly what the names of the functions are inside of the smart contract. It'll know their ABI. It'll know how to encode and decode results. It'll know how to poll for the right events and listen for them. And then you'll write a third program, which is the front end, that actually provides the user experience, and it'll have high-level operations like make a trade, and it'll have UI components like see what trades are happening. And of these three programs, the first two are really, really tightly interconnected, because every time you make a change to the smart contract, you have to make a corresponding change to that middleware layer. So what Reach does is Reach programs are the smart contract and the middleware layer. It generates those two parts, but we now have to say, well, how does the middleware layer interact with the user interface? And we do that by having the Reach program specify a interaction interface for the back end to call in to the front end to get information, feed it information, and so on. And that's what we see with these interact calls. So interact right here means that we're going to get information from the front end, we're going to get the hand that we want to play, or we're going to show the outcome of the game. Now, let's push this a little bit further so we can see the version that plays simultaneously and plays continually. So let's go over to that. This, by the way, is the, I'm sort of giving you a very fast summary of what is the tutorial on our site. So if you go to our documentation site, you can see a tutorial, which is a step-by-step walkthrough of developing this program, explaining every single line, every single piece of it going from a simple version to a more complicated version. Now this program is more like the way that I described earlier Shamir and I were to play, where Alice is going to make a challenge, Bob is going to accept it, and then we're going to enter a while loop. And in this while loop, we're going to continue playing whenever the outcome is a draw. We're going to play simultaneously. This is kind of a subtle point because on the blockchain, it's not actually possible to do anything simultaneously like it is in reality. And so because we can't do things simultaneously, we have to use the cryptographic commitment pattern to simulate simultaneity by making it so that one person does something first, but they do it secretly, and then they reveal only after another person has done their action openly. So this is a common pattern, and it's talked about in our chapter on trust and commitments. You should really think about the tutorial and the Reach documentation as not about teaching you Reach, it's about teaching you decentralized application development. And we try to use simple domain problems like how to run a proper rock, paper, scissors game. We try to use that simple domain to teach these fundamental Dapp programming ideas. So we use that commitment pattern here to have it so that Alice commits to her hand. And then what Bob does is he plays his hand in the open. And then Alice reveals her hand, and then we compute the winner of the game. And if the winner is ever not a draw, then that means it will exit this while loop, and we'll be able to transfer the final winnings to the final winner. Now that right there is just the sort of like the programming model of Reach. And of course, behind the scenes, what happens is that we take this program and we're going to generate those components that I talked about. We're going to generate a smart contract. We're going to generate a middleware layer. And in fact, that middleware layer is written in our abstracted standard library that can interface with multiple different blockchains. And the smart contract will be generated not only for Ethereum, it'll also be generated for Algorand. And in the future, it'll be generated for other platforms as well. And then what we can do is we can write another program that is like a front-end program where you can write it in JavaScript, you can write it in Python, you can write it in Go. And this program right here is a short program that all its job is to use the Reach standard library to actually connect with the contract. The way you connect with the contract is one person deploys it, another person attaches to it, and then each party provides their interaction interface. So Alice provides a wager, Bob provides a function that accepts the wager. This is like a simple test program, so it just always accepts it. And then they both provide a way to get a hand, which I've written it so that they get it randomly. And then they can, see the outcome of the game. When we actually run this program, what happens is that, I'm just going to scroll up. What happens is that Reach not only compiles your program to these different backend artifacts, but it also is like a deployment and testing tool. So you don't have to install Truffle, you don't have to install your own Geth instance, you don't have to inspect the actual blocks that get generated or anything like that. When you run Reach Run, what that's going to do is it's going to start a custom Ethereum or Algorand DevNet on your machine, and then have this program connect to that and run your test instance. So we can see that it started the test program, and then it'll go through and it'll actually run and show us all the things that happen. And it'll tell us, okay, the balance changed from 10 to 5 and 10 to 15, because in this version of the game, Bob won. Now, one of the things that is the most exciting thing about Reach is that it uses formal verification to check your program for mistakes. Let me just say just a little bit about how that works and what I mean by that. So if I were to give you a C++ program, and I could say, like, what is something that should be true of every C++ program? It's kind of hard to actually answer that question. Probably the only thing that should be true of everyone is that it should have no null pointer exceptions. I don't need to know anything about what your C program actually is doing, but I know that it shouldn't have null pointer exceptions, and it shouldn't overrun memory. So those are examples of general properties that are true of all programs category, namely the category of written in C. Similarly, blockchain programs should have the property that they don't try to overspend their accounts. And also they should have the property that they don't underspend their accounts, meaning that after the blockchain program runs, it shouldn't leave money on the table, because if it did leave money on the table, then that money would be totally inaccessible because the program is over. That means that there are no more future steps that could possibly give it back. I'm sure that we've all heard of examples of programs where they made a mistake and they made it so that the money is locked away forever. So we can actually see that property being checked right here. So right here, what we're doing is we're saying, whoever the winner is, transfer 2 times the wager to that winner. What if I were to change this to a 1? If I change it to a 1, then that means that 1 slice of the wager is being left in the account. And this means that my program has an error. So let's go down and recompile the program and see what happens. My computer runs really slowly when I'm doing video encoding. I just got another computer. It's sitting here next to me, but I haven't set it up yet. But it's a good opportunity to get a drink. If you were to run this on your computer, or if you were to run it on a computer that wasn't slow like mine, it would finish instantaneously.
I just wanted to add a question about in the meantime.
Sure.
So what chains does Reach currently support? And another question on top of that, are all programs deterministically the same when they are built and run? And is that always the case? Like if I have an Ethereum version of it, the Algorand one will behave exactly the same way? Okay.
So right now we support EVM protocols. And I say protocols rather than chains because, we also, can target layer 2s that use EVM, like Matic and off-chain labs and things like that. And then we also support Algorand. So those are the 2 that we support right now. And in principle, we could support pretty much any chain. Right now, supporting new chains is not really a technical question. It's more of a business proposition to partner with that chain. Now, when you say, do they behave deterministically, i.e., do they behave the same? They don't behave the same because they don't behave the same because different chains, different backends may have different rules about things like sizes. So, for example, on Algorand, integers are 64 bits, and on Ethereum, integers are 256 bits. So that means that when you write the program, you are writing a program that simultaneously works on both of them. So the Algorand version uses 64-bit numbers, and the Ethereum version uses 256-bit numbers. And you can write your program to be sensitive to this by looking at a variable that's called uint.max. So you can see how big the number is, and so you can make your program behave differently on one versus the other. Actually, really the right way to think about it is that by default, you have to write your program so that it is generalized over the size of integers. So you can't write in your program a large constant, because if you were to write that large constant, then it would not be in the intersection of those different backends. So you can say I want to write my program and have it be verified separately for each one, and then you could. Now, aside from that kind of little sort of platform issue, yeah, they behave the same. Now, there's another notion of determinism, which is different than, which I don't think is what you're talking about, which I'll comment on in a moment. But the compiler has finished, and let's just look at it real fast. So we'll see that I messed it up. I put a 1 times wager right here. And if we go look at the output, it says, right here on line 88, which is the end of the program right here is this exit, there was a theorem, and this theorem said that 0 had better equal the balance at the end of the while loop minus 1 times the wager. And what if the balance were 2? It could be 2, because the wager could have been 1, and that means that the balance minus 1 times the wager would be 1, and 1 is not 0. So you left money around. So what Reach does is that while you run your program, when you compile your program, it builds a system of equations that correspond to the behavior of your program. And if that system of equations has a solution, then your program has an error, and it will tell you exactly the variables, the assignment of variables to values that would lead your program to have an error. Now, what I just showed is just the checking of the general property being the null pointer exception property, the property that should be true of all programs that are blockchain programs. But you can also write in Reach properties that are specific to your domain. So for instance, at the top of this program, I have the definition of how to determine the winner of a game of rock, paper, scissors. And we can write assertions that are like test cases that say, well, if I run it on rock and paper, it should be Bob's the winner. But I can also write more general properties like, for all integers that I'm going to call hand, winner of hand and hand is equal to draw. So that is a general property that is something that is really specific to my program. But it's also something that's not really feasible to actually check because, hand, as we just established on Ethereum, is, 2 to the 256. So that's a really large number of possibilities. And Reach does not try every single one. Instead, what it does is it builds a system of equations where we determine what it is. Now, I want to look to some of the questions that people have asked because they're related to what I'm talking about. So Lev says, how are while loops able to be checked deterministically? I assume that what you're saying is, I know that while loops are dangerous to check because isn't there this thing called the halting problem? How do I know if they're going to really have the properties that you say they are? Because how are you reasoning about the program terminating? Things like that. While loops, well, first of all, Reach programs are guaranteed to have a finite amount of computation over the course of a potentially infinitely long chain of communication. So that's a very complicated way of saying that basically every individual step of a Reach program is guaranteed to be finitely long. And because each step is finitely long, we can reason about those individual portions completely. Now, the next thing is that when you use while loops, you write down loop invariants. So one way to verify while loops is called bounded model checking. So let's imagine we have a while loop where before we have the before part of the program, then we have the while loop, and then we have the after. One way to verify that is to say, well, would the program be true if we did before and then after because the while loop didn't run? Then you check that. Then you can say, well, let's check it if we did before the while loop one time and then after. That's one. Then you would do, what if I did before and then the while loop and then the while loop again and then after? And that would be 2. And there's obviously a countable number of these things. And if the while loop can potentially go on forever, then you'd have to check all of those. And that's what bounded model checking is. Many verification tools do bounded model checking. You may have heard of the Firefly tool by Runtime Verification. They talk on their site that explains how Firefly works, how they do bounded model checking. It's sort of the standard thing to do when you don't know what the while loop is supposed to do. And what Reach does is by having you write down simple loop invariants about what the purpose of the loop is, we can now break up this reasoning into 3 separate proofs. Does the before part of the program establish the invariant? If the invariant is true, does the body of the loop reestablish the invariant? And does the invariant and the negation of the condition prove the after part? So we have those 3 proofs, which is a finite number of proofs, and those are the ones that we check. Now I'm just going to look at the Q&A question. Yeah, so someone says what changed, so we just answered that.
Cool. I think a good question to ask at this stage would be like, how does one get involved with Reach? And could you elaborate a bit more about the bounty program that you guys have been running in the past?
Sure, yeah. There's just a follow-up question on the invariants. The invariants are provided by the programmer. The Reach does not synthesize them. There are actually there's this whole body of work that's been around for maybe like 30 years on synthesizing loop invariants. And in the future, we will probably add something to do this. But really the way to think about it is that you're going to start off your program by having the loop invariant just be true, and this is trivially true. But then you'll write your program, and then there will be assertions that will fail. And then you will gradually add things to the invariant that to slowly discover what the invariant is. Because like, if the tail of your program like looks at the balance, then you'll say something about the balance. If the tail of your program looks at some other variable, then you'll say something about that, and so on. So yeah, writing the invariant is part of programming. Okay, now how do you get involved in Reach? I mean, if you're interested in it, the first thing to do is to go to the documentation, which is at docs.reach.sh. You can look through the overview, and the overview is like a really high-level perspective on like, what is Reach doing? You know, it talks about this high-level programming, it talks about verification, it talks about deployment. And then you can go do the tutorial, which is this very incremental step-by-step activity. And then after that, then the documentation really opens up quite wide. You can read about the guide, which talks about kind of the whys and how Reach was designed. There's something that we call the workshop series, which, you know, the tutorial is like, let's tell you every single line of the program. The workshop is more like, go try to write this program, and then come back partway through and we'll give you pointers, and then go back and do a little bit more. So think of that as like, you know, the tutorial is the lecture, and then the guide is like the homework. Sorry, the workshop is the homework. And then of course there's the reference. And of course, the best way to get involved in the community is to join our Discord community, where you can talk to other people who are working on Reach. Now, you mentioned this bounty hack thing. So Reach is one of the scouts of what's called the Algorand Scout program. And the Algorand Scout program is basically a grant program funded by early investors in Algorand, where they want to promote people writing interesting programs that can deploy on Algorand. And so what we have done at Reach is we've run a, we did one instance of it, basically a month-long, what we call the bounty hack, and we're going to be doing more of these, probably once every 2 months, and then once we have more resources, we'll do it every month. What the bounty hack is that rather than saying to you, come up with your blockchain idea, we're going to give you a wide variety of interesting blockchain ideas that they're not necessarily new companies that you can go form, but they're programs that haven't yet been written in on the blockchain. And then you'll write them, and then there's you'll present them, you'll work with other people, you can write explanatory content about what you did, so you can write like tutorials, workshops, and there's this whole incentive structure where the participants in the bounty hack will all vote on whoever they think was the coolest program at the end of the month-long process. The first one that we did, the winner was someone that made basically like a Twitch plays Pokemon, but on the blockchain, where you can like pay to have the single instance of the Pokemon emulator make a certain sequence of moves in the game, and then they launched that on Algorand. Another person, actually a like 11-year-old kid, did a version of tic-tac-toe where like every spot on the board cost a different amount of money based on how like valuable that thing was. So you're basically playing a game of tic-tac-toe where you're not only wagering, but you're sort of like, you're not only trying to win, but you're trying to win efficiently because certain parts on the board are more expensive, like clearly the middle is more expensive. So those are just like two examples of like, fun programs where it can be kind of stressful to walk into blockchain and say, all right, you are now expected to compete with Uniswap tomorrow. And that's what it means to be a blockchain programmer. And of course, Uniswap already exists. And it's very difficult to compete with Uniswap tomorrow. And people may not have their own bespoke ideas, their own particular things that they want to do, but they still want to get involved in blockchain. And so we want to give them non-trivial, but still beginner problems that they can build. And a lot of these are a kernel of something more. So even something like the Pokemon thing, right? Like, probably there's not going to be a business launched tomorrow about Pokemon on the blockchain. However, fundamental components of how that works is very similar to how you might build something like a censorship-resistant Twitter, because what you're really trying to do with a censorship-resistant Twitter is have a trustworthy place where you can make non-reputable announcements. And that's kind of what's going on in the Pokemon program, because you're announcing the moves that you're trying to make. And we can think about what is the authoritative sequence of those actions. So anyways, each of the programs in the Bounty Hack has a component of it, which is a deep principle of blockchain programming.
Cool. That's a great. I think that's great insight. And I think Chris also posted about the Google Doc where you can learn more about it in the chat.
Yeah, and then the Algorand Scout program, they also, we're not only doing the Bounty Hack, but there's also this larger thing where if you do have like a particularly powerful idea, then you can apply for that. So I believe that someone has recently applied for making like an NFT generator that works on Algorand and something like that. So yeah, so this is if you're interested in free money and you want to learn Reach, it's a great opportunity, especially because you can launch on Algorand.
Yeah, that's fascinating. I guess as a final question, because we're almost out of time here, where do you see the future of Reach being, and do you think it will be eventually, like overtaking Solidity as like the prime choice of even EVM development?
So the goal of Reach is that in the long term, when people think about what blockchain is, they will think about what Reach is, as opposed to thinking about what underlying consensus networks are or things like that. So as an analogy, if I were to ask my my grandmother or my mother-in-law to describe a computer to me, she's not going to describe the Intel x86. She's not going to describe the PCI bus. She's not going to describe TCP. She's going to describe Windows. And maybe she won't even describe Windows. Maybe she'll really describe a web browser. And that means that although in the history of computing, hardware has been very exciting and a place where a lot of innovation has happened, it actually is not the thing that is the ultimate product that people who care about computation care about. They don't care about CPUs. That is not the product that is being used widely by the world. And I think that consensus networks like Ethereum and Algorand and all the other different ones, Cardano and Tezos and Elrond and things like this, I think that these in the long run are like Intel. They are important companies that will be a foundation of our economy and our computational infrastructure for the long term, but they don't have the user mindshare that the actual applications will. And I think that the big question is whether that mindshare will be held by applications, like, say, Uniswap as an example application, or whether that will be held by something else, which is more like an operating system. And so our perspective on Reach is that our goal with Reach is to be that operating system for the future of blockchain. That is right now, we are providing an abstraction layer that allows developers to build applications that are not really feasible to build today directly on Ethereum using Solidity, because it's too complicated to build them, and it's too complicated to build them correctly. And so by providing this abstraction layer, we're basically simultaneously lowering the floor to entry into blockchain by making it so that even 11-year-old middle school kids can build blockchain programs that are truly unique. And we're also raising the ceiling on blockchain development because we're making it so that by having the automatic formal verification there every step of the way along the compilation process, you can do things that wouldn't have been feasible before. So by expanding this audience, we're making it so that a vast new number of people can come into the blockchain world. Now, there are very few existing blockchain developers, the traditional people using Solidity. And I would say that I think that Reach is extremely valuable for them, but honestly, it won't really chuff me very much if they never use Reach, because there's only a couple thousand of them when there are tens of millions of developers in the world doing other things. And we need to ask ourselves, as people who are passionate about blockchain, whether or not we are satisfied with there being thousands of blockchain developers, or should there be millions of blockchain developers? My opinion is that I am a blockchain, maximalist, you might say. I think that the future of blockchain is extremely bright, but it is bright in a way that is extremely boring. Now, what do I mean by that? Right now, no one is excited about double entry bookkeeping. No one is excited about insurance. No one is excited about TCP, and no one is excited about the HTTP protocol. Yet those four things have done more to change our lives than many, many other things. But they are fundamental technologies now that we think of as boring because they are so pervasive. And I think the future of blockchain is that. The future of blockchain is something that will be so pervasive in all avenues of our lives that it'll just be a fundamental way about how we think about how distributed systems work and how we think about systems in general work. The same way that we take for granted, if your friend tells you they're starting a company, you don't have to ask, does your company have a website? Or is there a server associated with your company? The answer is yes. And so I think that in the future, it will basically be an assumption that all organizations have at their core component some decentralized application, because it will be more efficient than the centralized applications right now that are weighed down by middlemen taking their cut and raising the transaction costs for the rest of us. So the vision of Reach in the future is that vision. And that is a vision where there are millions of blockchain developers, and we cannot get to that place if the only way to do blockchain programming is with this extremely low-level programming mentality where you have this non-uniform memory hierarchy. We have to deal with the very complicated decisions about what exactly you do with the funds, how do you make sure that there's not stuff left over, and how do you deal with this implicitly constructed state machine that you have to have in the background but is never really apparent in the program. So that's the vision of Reach.
Well, seems like a very ambitious goal. And I do think Reach is primed for this growth that it's coming to blockchain. I'm personally noticing a lot more people showing interest in blockchain, especially locally and stuff. And it starts from all these market cycles. You have NFTs, you have DeFi, but ultimately you get a lot of new developers that are interested. And it'll be great for them.
I don't think that we will reach that high vision that I talked about if the only thing that exists are speculation cycles of tokens and NFTs and DeFi. Those things are really exciting, but they are not what blockchain is. Blockchain is much, much bigger than that. Blockchain is the sort of, in the same way that another analogy that I really find appealing is when I was a kid, we didn't have smartphones, but there were cell phones, and some cell phones had really simple programs that you could run. And of course, every cell phone was a computer. It just was a computer that was not set up to allow anybody to develop for it. Many people think that the thing that's special about the iPhone is that it has a touch screen. And yeah, the touch screen was a really big innovation. But the bigger thing that was innovative about the smartphone and the iPhone was the App Store. And the thing that made the App Store special is that it made it so that anybody could build an embedded device. It used to be that you had to have hardware expertise. You had to have low-level programming expertise. And you had to have huge capital to be able to actually produce a device and get it out there. But what the App Store did was it made it so that everybody could be an embedded device developer because they could make their application for this embedded device that everyone carries around. And that's what Reach is. Reach is the App Store for the blockchain, because right now, the blockchain can do everything today that it will be able to do in 50 years. I don't think that there are any fundamental new innovations that are going to come out. I think that, if we were talking in the world before there was proof of stake, that we would say, yeah, we got to discover some new stuff. But proof of stake is the answer to basically the major technical problem that there was. So now that we've solved that technical problem, the only thing that is standing between what blockchain is today and what blockchain will be in the future is developers. And the existing plan that people are using to bring people into the blockchain space by teaching them Solidity with cute video games is not going to bring in millions of people, because it's just a fundamentally high floor, low ceiling way of programming. And what Reach does is it makes it so that there's this extremely low floor and this extremely high ceiling, and that will have the App Store effect of bringing in many, many more people. And those people will come up with totally creative new ideas that will not occur to any of us who all we care about is DeFi and NFTs, because that's what we see every day.
Right. That's a great analogy. And I think I'm really looking forward to seeing a lot more devs come in and them potentially just using Reach as a way to get into blockchain development. Do you have any closing comments before we end this session? We're almost above time now.
I don't really feel like I have any closing comments. We can, ask more questions. I don't know what your time frame is. But yeah, I think that we've had a great, I feel like, we're in Return of the King. I gave you the end for Reach. We gave you the vision of Reach, and now we're like the vision of blockchain. So we got 3 different endings.
I think we had a good question in the chat. If you want me to read it out.
Okay.
James says, how does encouraging dumb programmers to attempt and solve hard problems help everybody though? The idea of a junior developer working on anything critical to finance, business, relationships, or even basic event tracking is horrible. Why not have community vetted and curated templates or tried and tested C++ with EOS? Colleges are teaching C++, so the juniors are learning that too. Solidity for Ethereum also has 100,000 beginner courses now. So many questions.
Sure, yeah. I think that you could argue that it is too difficult to build a memory-constrained program that runs on a hard real-time system that has to be responsive and consume a very small amount of battery. That is what, if I were to ask somebody in 2005, I'm going to make it so that anybody can write these embedded programs. People would say, no, you're crazy. Like, embedded programs, you need expertise to be able to do that. And one of the things that the smartphone did, that the iPhone did, is it made it so that there was a safety net beneath all of those things, because it had ways of, and I think actually Android did this a little bit better. There were ways to analyze, run in a virtual machine that protects the program from misbehaving in ways that are dangerous in that embedded landscape. And so I think that one of the main things that Reach does is by building in the formal verification with every step of the program, and by providing a high-level programming language, the things that make blockchain development difficult are just simply not present. So because they're not present, it makes it so that it's much easier to actually do. So I think that James has a really good point, that if we have dumb programmers trying to do really hard things, then we should not expect them to succeed. But I think that the tens of millions of developers in the world are not dumb. Yes, there are many people who have learned extremely basic programming, but I do not believe that the vast majority of programmers are not involved in blockchain simply because they're not interested or they haven't heard about it. I think that they are really intelligent and capable programmers, but the development environment is just extremely low level and extremely difficult to actually get involved in. And that makes it so that it's very difficult to actually do things. Yeah, I think that would be my answer to that question. Now, I did want to comment just one, so why not community vetted and curated templates? I think that this is what I'm talking about by saying that the way that blockchain is going to blow up is that if there are many kinds of programs that you and I haven't thought of, and that requires a huge number of developers to try things out and discover what is necessary. Imagine that, again, I like using the smartphone as an example, but let's just forget about that for a moment. Imagine if we're, back in the 60s when there's the first time that people had programs. I think that people would have really said back then, well, there are really only 5 different kinds of programs. You have your dynamic system simulation, you have your accounting program, you have your compiler. There's like just a few programs that we could write all the programs down, and we just need to write, the best version of each one of those, and then we don't need any more programs. But whenever we think that we have solved every problem, just give people the opportunity to explore, and they will find things that you absolutely did not think of.
Yeah.
Someone in the chat mentioned Marlowe. I think that Marlowe is a really great example of something that is really similar to Reach. For people that don't know, Marlowe is basically like a drag and drop tool for making smart contracts that behave very similar to basic financial instruments. And a way that I like to think about Marlowe is like Excel. Excel is actually the most popular programming language in the world, but we don't often think about it as a programming language because people who are in computer science and do programming tend to denigrate those who can only use Excel, but actually it really is a programming language that has very amazing features, and people can build their own applications in Excel. And but it has a totally different mindset about how you're supposed to program, and that mindset influences the kinds of programs that can be made. But the kinds of programs that can be made are still extremely wide-ranging for what people want to do. And the way that I see Marlowe is an attempt to cut up a particular domain, financial instruments, and build a really easy, sort of WYSIWYG style graphical tool that allows you to build programs like that. And I think that that's really great. And I think that there should be, they recently added, Lambda to Excel, which is pretty awesome. So anyways, so I think that something like that is a really great tool to exist. And I think that it makes a lot of sense to have these curated templates for certain categories of DApps. But, when we show something like, I don't know, like Doom ported to Excel, I don't know if that actually exists, but there's Doom ported to everything, huh? The reason that we're pointing that out is because it's so audacious and strange, not because Excel actually is a great tool for building, like a roguelike game or something like that. And so I think that there's definitely space, and I think that in the long run, there's going to be lots of these tools. But right now, I feel as though the existing blockchain programming languages, they are sort of in between assembly and C. And there's no JavaScript and Python. There's not even really a C, and there's certainly no Excel. And I sort of see in the future, we have things like Marlowe, they're at that Excel level. Reach attempts to be at that JavaScript Python level. And I think that some of these second generation blockchain programming languages, like Viper is an example of this, and Clarity is an example of this. They attempt to be in that C space where they try to avoid the things that make Solidity kind of in between assembly and C, but they don't fully provide a high-level programming abstraction. By the way, right now in the last little bit, we're really getting into the, sort of the world according to Jay. We're getting further and further away from what Reach is. A lot of these ideas are just, hopefully interesting things that you may find about the blockchain world. And I hope that you'll be able to, go explore the concrete things of what we've provided right now and Reach for you to explore these things. And we can talk about these long-ranging ideas, on our Discord later if you're interested in that.
Okay, hi, I'm Alexis from Dapp. So we are a bit over time. So maybe we can go to the networking station. Thank you so much for coming, everyone. It was a pretty great talk. I'm dropping off some links if you want to follow Dapp on Twitter or become a free Dapp member. Is there anything you want to share with us, Jay, on the channel?
I think that the Twitter is great, and the documentation that I have up here on the screen. And then from there, you can find links to how to download and install Reach and how to get on the Discord and everything like that.
Okay, thank you so much for coming, and see you in the networking session.
Later, everyone.